In the last segment, we looked at how to design a domain model that uses event sourcing. In this section, we're going to take a look at an actual code example, the place order use case, where there's two services, an order service and a customer service. And you're going to see how the code actually looks in these microservices. So in the previous section, I described that there were several different programming models, some functional, some object-oriented. And in this section, I'm going to show the object-oriented version. So it's Java code, sort of standard mutable domain objects. So if you think about object-oriented programming, the big idea there is that you have objects that encapsulate state and behavior. So if we look at the customer aggregate, it has fields like a credit limit and credit reservations that's a hash map of order ID to order total. So it represents the actual reservations against that credit limit. And then the behavior is represented by two kinds of methods. A process method that takes a command and returns a list of events, and an apply event method that takes an event and updates the state of the aggregate. So we've kind of structured the domain logic in a slightly different way. So you could actually think about how you would do this in using a standard approach. You'd have a method such as reserve credit that takes the order ID and the money. It does some verification, including the credit check, and if the credit check succeeds, then it updates the state. So in this model, we're doing it slightly differently. That method is actually split into two. The process method that takes the command returns the events that encapsulate that state change. And then there's an apply method that takes the event and updates the state. So it's kind of a similar business logic. It's just split into two different methods. So it takes a little bit of getting used to, but it's not that much of a change. So the actual underlying framework defines a couple of base interfaces, and the actual underlying framework's written in Scala, but I think even if you're not familiar with Scala, they look very similar to Java interfaces. So there's an aggregate trait that encapsulates the mechanism for applying an event. So there's an apply event method that takes an event and gives you back an updated aggregate. So that can be used in both a functional case where it returns an updated copy of the aggregate, and an in-place update approach where it simply returns this. And then there's a command processing aggregate that extends aggregate and adds the ability to process a command. So there's a process command method that takes a command and gives you back a sequence of events. The actual reason for this split is because the event store only needs to know about applying events, how to reconstruct the current state of an aggregate. It doesn't need to know about command processing aggregate. So it's kind of cleaner separation of concerns. And then to support this mutable object-oriented programming model, there's this wonderfully named class called reflective mutable command processing aggregate. Bit of a mouthful. But the big idea here is that it implements apply event and process command by using reflection. If you didn't use this abstract class, what you would actually have to do is write a lot of conditional logic, where you'd say if the type of event is this, then do that, else if it's this type, do something else. Likewise for the process command method. This class just implements a simple reflection-based dispatching mechanism. So apply event takes the class of the event and looks for an apply method with that parameter type. Similarly, for process command, it looks for a process method that has a parameter type that matches the type of the class of the command, and then just invokes it. So that's the high-level framework that's supporting these aggregates. Here's the actual customer aggregate. So you can see that it's got a credit limit field, reservations field that's a map. Then there's some business logic such as available credit that just uses the nice Java 8 Streams API to sum up the credit reservations and subtract that from the credit limit. You can see that it extends reflective mutable command processing aggregate and defines some process command methods. So there's the process command method that takes a create customer command and returns a customer created event. That's very simple, just sort of pass-through logic. The process command method that takes a reserve credit command is a little bit more interesting. It actually contains some business logic. So it's saying if the available credit is greater than or equal to the order total, then return a customer credit reserved event. Otherwise, if the credit limit check fails, then return a customer credit limit exceeded event. So we've actually implemented some business logic in there. Then moving on, if we go look at the apply methods, there's two of them. There's apply that takes a customer created event, and it basically functions as a constructor. It initializes the credit limit and sets the credit reservations to an empty map. The actual apply method for customer credit reserved event puts an entry into the credit reservations hash map. And then the apply method for the customer credit limit exceeded event does nothing. That doesn't actually represent a state change, so it actually doesn't need to update anything, but it still has to be able to apply that event. So that's an example of an aggregate. So you can see how a standard method that would do some verification and an update is now split into a process method that does verification, returns events, and an apply method that updates the state. Moving up the stack ever so slightly, here's an example of a service. So this is the order service, and it has a create order method that creates an order for a given customer, and I'm just passing in the order total. I'm not worrying about line items in this example. And it just creates a new order in the event store. And it's actually written in terms of a helper class called aggregate repository. And that's a parameterized type, and it takes two types, the order, the aggregate type, which is the order, and the command type that is order command. And it has methods such as save. And what the save method does is under the covers, it creates the order aggregate, it processes the command, it applies the events, and then it persists the events in the event store. So it's encapsulating the boilerplate logic of creating an aggregate. You could actually use the event store API directly, but you'd get pretty tired of writing the same code over and over again. So here's an example of some event handling code. So this is actually written in the context of a Spring application. And so it's leveraging some annotations. So the @EventSubscriber annotation identifies this class as defining event handlers, and its ID member specifies the name of a durable subscription to the event store. So if the client is disconnected, it will get the events that it missed when it reconnects again. And then the actual event handler class defines one or more event handler methods that are annotated appropriately. So that the reserve credit event handler subscribes to an order created event, and it basically tells the customer to reserve the credit. And it's written in terms of the event handler context, sort of helper class, that has methods such as update that encapsulates the process of updating an aggregate. In this particular example, it loads the customer, processes the command, which is the reserve credit command, applies the events that result from that, and then persists the events in the event store. It's analogous to the aggregate repository. but this is used in the event handling scenario. So that's the code example, and I encourage you to go look in my GitHub repository to actually look to grab the complete application, and so that you can look at it in more detail.